Hi students, so in this session we are going to see linear areal volumetric expansion. Okay, in thermometry, okay, already we have seen the change in scales, then how thermometer works, on what principle thermometers work. Okay, then now today in this session, in thermal expansion itself, how in solids, okay, in solids, like how linearly, if we increase the temperature, the dimension, length dimension, or sometimes area itself or volume of the body will change. Okay, so for that we will see some relations. So first one is linear expansion. Say L is equal to the final length. Suppose if we consider a length, L is the final length. L is equal to its initial length into 1 plus alpha delta theta, where L is the final length, that is the length after increasing the temperature. This is the initial length. Okay, and this is the coefficient of linear expansion. The coefficient of linear expansion, and this delta theta is change in temperature. Change in temperature. Okay, change in temperature. So first one we have seen linear expansion. So linear expansion, L is equal to L naught into 1 plus alpha delta theta. If we make a 10 degree Celsius change in temperature, then this is going to be 10 degree. Theta 2 minus theta 1 is 10 degree. Then if a material is copper, it will have a constant value for coefficient of linear expansion. Okay, so based on the material, a change in length will happen. So this is the final length, this is the initial length into 1 plus alpha delta theta. First I shall introduce all the expansions, then we will discuss a little bit more into its details. Suppose then areal expansion. Areal expansion. Areal expansion means what will be the final area. So same structure, same formula. Okay, so A is equal to A naught into 1 plus beta delta theta. So this time I need not write everything. This is final area, this was the initial area. Now when we change the temperature, this area became this 1 plus beta delta theta. This is change in temperature. This is coefficient of areal expansion. Coefficient of areal expansion. Clear? Then third one, volumetric. So volumetric expansion, same structure, same formula. Okay, so V is equal to V naught into 1 plus gamma delta theta. So it was 1 plus alpha delta theta, now it became 1 plus beta delta theta, and here for volume this is 1 plus gamma delta theta. Final volume, initial volume. Okay, is it clear? Please note it down. Okay, these are the respective formulae for area, for volume. Okay, clear? Fine. Okay, there is a relation between alpha, beta and gamma. Okay, let us see that. Okay, alpha, beta and gamma. Okay, coefficient of linear expansion, coefficient of areal expansion, coefficient of volumetric expansion, and that depends on the material. Okay, so we know L is equal to L naught into 1 plus alpha delta theta. Let it be here. Then area A is equal to A naught into 1 plus beta delta theta. this is, suppose if you take a square plate, so if we increase its temperature, each side will increase, each side will have its change based on this formula, okay, this formula. And if we consider the total area, that the total area change will happen based on this formula. Okay, now let us see. So can I put the final area as L square? Suppose if we consider, okay, a square plate of length L, so this is going to be L square. Previously, say for example, its area was this, okay, this is L naught. We increase the temperature delta theta. Now what is happening? L square is equal to, we can say this is area naught, okay, if its area is A and its area is A naught. So area naught is what? L naught square into 1 plus beta delta theta, right? So what about L square? L square is like this. L square is equal to what? L naught square into 1 plus alpha delta theta, and L square is equal to L naught square into square A plus B all square form, A plus B all square form, A square plus 2AB plus B square. So A 1 plus 2 alpha delta theta plus alpha square delta theta the whole square. So here this alpha, okay, this is very small value actually, very small value, okay, alpha's value is very small, so we can neglect this. If we neglect this, we will be getting L square is equal to what? L naught square into 1 plus 2 alpha delta theta. Now you can see here, comparing this equation and this equation, when you compare these two equations, the only change is here, 2 alpha beta. So we can conclude that beta is equal to what? 2 alpha. Take this relation. Clear? Beta is equal to 2 alpha. Note it down. Fine. Shall I raise? Okay, pause the screen and note it down. Okay, so same way, in the same approach, if you do, L is equal to L naught into 1 plus alpha delta theta. Same way, volumetric expansion V is equal to V naught into 1 plus gamma delta theta. Okay, so if we take a cube, okay, previously the cube was like this, okay, cube was like this. When we increase the temperature, now the cube became, okay, so much difference will not be there, but still a little bit difference will be there. So if this is the volume V naught and if this is the volume V, we can say if each side is L, V naught is L naught cube and V is what? L cube. V is equal to L cube. So this is, we can say L cube is equal to L naught cube into 1 plus gamma delta theta. Now let us take the cube of this. L cube is equal to L naught cube into 1 plus alpha delta theta the whole cube. So you know this equation, A plus B all cube is equal to what? A cube plus 3A square B plus 3AB square plus B cube. Okay, so same way we will approach L cube is equal to L naught cube into 1 plus 3 alpha square delta theta plus 3 alpha delta theta square plus delta theta cube. So this will be the expansion. So in this already I have mentioned here alpha is very small value, so this can be neglected. So L cube is equal to what? Now L naught cube into 1 plus 3 alpha delta theta, the okay, 3 alpha delta theta square. Okay, did a mistake here. This is like 3 alpha square delta square, and this is 3 alpha delta, because 1 is the term, right? So here 3a square into b, so here 1 is there and here 1 square is there, so that is a mistake. So L naught cube into 1 plus 3 alpha delta theta. Okay, so b cube is what? 1 plus, so here alpha cube delta theta all cube. Fine. So this also can be neglected, so this will be the form. So when you compare this equation and this equation, we will be getting what? Alpha gamma is equal to what? 3 alpha. Okay, so this is another equation, another relation. Clear? Okay, clear? Noted? Fine. Shall I erase? Pause the screen and note it down. Okay, so here finally we can conclude that gamma is equal to what? 3 alpha, and beta is equal to what? 2 alpha. Okay, so remember this relation. Clear? Okay, so based on this relation, okay, questions can come. Okay, fine. So okay, so here there are many applications based on this expansions. Okay, certain applications we will see. Based on those applications, very good numericals are also there. Okay, so first application is number 1. Okay, is like already we have seen the time period of oscillation of simple pendulum. Okay, if a simple pendulum is swinging, it will have a time period. Its time period is what? T is equal to 2 pi into root of L by G. This is the time period of simple pendulum. Time period of simple pendulum. Now if we increase the temperature, so here this is time period. Okay, I am not going to use delta T for change in temperature. So in order to avoid this confusion only, we are using delta theta. Okay, delta theta we are using. So if there is delta theta, that is temperature is increased or decreased, temperature is increased or decreased, what will happen to this L? L varies. The length of the pendulum will vary. If we increase the temperature, the length of the pendulum will vary. So a slight change in this length of the pendulum will definitely affect the time period. So how much will be the change in time period? How much will be the loss in time? How much will be the gain in time? Okay, all these things we need to see. Okay, so let us see. L is equal to what? L naught into 1 plus alpha delta theta. So this change will happen to time period. Okay, based on this change in length, there will be change in time period also. Okay, so let us do in this way. T is equal to, how much will be the change in time period for the change in length? So T is equal to 2 pi into root of L by G. Like taking natural logarithm of t is equal to natural logarithm of 2 pi into root of L by G. Okay, now when we take it inside, natural logarithm of t is equal to natural logarithm of 2 pi. Now when we multiply in logarithm, we can take plus. So natural logarithm of root L can be written like 1 by 2. This is division. So minus of natural logarithm of what? G raised to 1 by 2. Clear? Now we will differentiate this. When we differentiate this, we will be getting okay. When we differentiate this, we will be getting the differentiation of logarithm of t will be 1 by t dt, and when we differentiate natural logarithm of 2 pi, that will become 0, and here when we differentiate, what will happen? This is equal to plus 1 by 2 differentiation of natural logarithm of L. Okay, what we will be getting? 1 by L dl. Okay, then differentiation of this is constant value, and this also will become 0. So finally what we are getting is 1 by t dt is equal to half into 1 by L into dl. So if you write like this, dt by t, what is this dt? dt is nothing but change in time period. Change in time period divided by original time period is nothing but fractional change in time period. This is equal to half into, this is change in length, dl divided by L. So the fractional change in time period is equal to half into the fractional change in length. Okay, clear? Note it down. So fractional change in time period is equal to half into fractional change in length. Okay, copied. Shall I erase this? Okay, so we can write this as fractional change in time period. Okay, this is equal to half into fractional change in length. Fractional change in length. Okay, done. Right, now suppose if we write L is equal to L naught into 1 plus alpha delta theta, if we multiply it inside, L naught plus L naught alpha delta theta. Now if we bring it here, L minus L naught is equal to what? L naught alpha delta theta, and we can write L minus L naught divided by L naught is equal to what? Alpha delta theta. So this is actually what? Change in length by original length, or in this term, if it is very short value, small value, dl by L, nothing wrong in writing like that. So are you able to follow this relation? Okay, so from this formula I have taken the fractional change in length. Fractional change in length is equal to alpha delta theta. Alpha delta theta, the coefficient of linear expansion into what? Theta. Okay, so in this way, what can I write? I can reframe this equation in this form also. Fractional change in time period is equal to half into fractional change in length. So this can be written like alpha delta theta also. Okay, we do not know what kind of data they will be giving in the question. So this is also fine. Okay, 1 by 2 into alpha delta theta. What is this actually change in length by original length in the mechanical properties of solids? We have seen such thing, change in length by original length. What is this? We call them strain there. So we can say that this is nothing but thermal strain. This is thermal strain. Okay, so this is what alpha delta theta. Clear? Okay, shall I erase that? Okay, so all these are correct. Okay, fractional change in time period is equal to half into fractional change in length. dt by t is equal to half into dl by l. dt by t is equal to half into alpha delta theta, or delta t by t is equal to half into delta l by l. Everything is fine. Okay, clear? Now this dt is what? Change in time. So dt is equal to what? Change in time. We can write half into dl by l into t. So this is a change in time. Okay, or we can say change in time, or we can say this could be gain in time or loss in time. Okay, so if a time is given, like for 1 hour, how much is the loss in time or how much is the gain in time? If the length is increased, okay, then time period will increase. If the length is increased, time period will increase. There will be what? Loss in time. If length is decreased, time period will decrease and there will be gain in time. So likewise, based on whether it is increasing or decreasing, there can be gain or loss. That is nothing but change in time. So for 1 hour we need to multiply with 1 hour. Okay, for 1 day we need to multiply with 1 day. Clear? Okay, fine. So say for 1 hour, say for example for 1 hour, the change in time or loss in time is half into dl by l into in 1 hour how many seconds are there? In 1 hour 60 minutes are there. 1 minute is 60 seconds. So this much loss will be there or this much gain will be there for 1 hour. For 1 day, dt is equal to half into dl by l into 60 into 60 into 24. Okay, for 1 day. Or we can say dt is equal to half into dl by l into 86,400 seconds. Okay, say for 1 day. Okay, so because of the change in length, okay, the time period will have this many effects. Okay, hope it is clear for you. Done. So this is one application, one area which we need to understand. Clear? Okay, shall I erase this? Okay, fine. The next application is bimetallic strip. Okay, bimetallic strip. Second one, one is the effect actually. One is the effect, time period will be changing. Now this one is bimetallic strip. Okay. This is nothing but say bimetallic strip is two strips like this. Okay, two strips like this. This could be one metal, this will be another metal. Okay, suppose if its length is L, this its coefficient of linear expansion can be alpha 1, its coefficient of linear expansion could be alpha 2. Okay, please note it down. Okay, one is alpha 1, the other is alpha 2. Okay, so one will have more coefficient of linear expansion, the other one will have less coefficient of linear expansion. So suppose if we consider alpha 1 is greater than alpha 2. Okay, now if we increase the temperature, what will happen? This will start expanding. Since it's alpha 1 is greater than alpha 2, this will expand more. So when this expands more compared to this, generally what happens is this is completely connected. Okay, everywhere this is connected. Bimetallic strip is strongly connected everywhere. So when it expands, it cannot get detached. So what will happen? This one will curve outside, this one will be inside. We will be getting this kind of structure. Okay, this kind of structure will be getting. So this one, this is what alpha 1, this was alpha 2. This is going to be the effect. Things are going to be like this. Okay, and its length, everything will get changed. Okay, now one possible question what they can ask is based on this arc is equal to radius into angle. Okay, they can ask this length. Suppose if this length is r, okay, if its thickness is t1, if its thickness is t2, okay, and this angle is theta, we know arc is equal to what? Radius into angle. Radius into angle. Suppose if this length is L, if this is L1 and this is L2, if they ask L2, L2 is nothing but R into radius into this angle, no worries. Same way if they ask L1, if this total length is say for example x or t1 plus t2, then L1 will be what? R plus x into theta, r plus x into theta, or r plus t1 plus t2 into theta. Suppose if they are asking this length, up to this point, okay, then this is going to be what? R plus t1 is equal to what? This length should be given. Okay, here length will vary. So if this is L, then we can say L into theta. So based on the question, okay, we will have to carefully manage this. And definitely one thing which we need to keep in mind is what will be L1 and L2? L1 will be L into 1 plus alpha 1 into delta theta, and L2 is going to be L into 1 plus alpha 2 delta theta. And practically speaking, this L in this intermediate length will have some slight variation in the dimension, but they will not consider that and ask. Okay, either they will be giving this L as L1 or L2, something like that. Okay, then we will be able to manage them. Clear? If I note it down. Okay, so what is the application of bimetallic strip? Suppose if this is a switch mechanism, this is a bimetallic strip. Okay, they say for example length L, here alpha 1, here alpha 2. So if alpha 2 is greater than alpha 1, if suppose, okay, due to some reason, if the temperature increases, okay, if the temperature increases, what will happen? If this is the point where it is connected, this will become like this. Okay, this will become like this, and the switch will be here. It will not connect. The length will not reach this point. So in case if we are setting in such a way that if temperature increases, it should get switched off. Okay, in those kind of thermal sensors, okay, where we need to switch off the system if temperature increases, we can use this kind of bimetallic strip. So here it will bend and it will get connected off. Okay, clear? Okay, so this is about the thermal expansion in solids, children, and two applications we have discussed. Again, further we need to discuss some more things in this expansion, linear, aerial, volumetric expansion. Certain more applications, certain more areas are there to discuss. Okay, so again we will discuss its problems in another session. Thank you. Okay, goodbye, good luck.
Hello, students. So, today in this session, we will do some problems on thermal expansion, especially thermal expansion on solids. Okay, in the introductory lecture, we have seen certain points. So, one of the point is when you apply heat to a substance, which is a rod or plate or any three-dimensional object. Suppose if the length is varying, okay, based on the temperature difference. If the temperature difference is delta theta, we know new length is equal to old length L naught into 1 plus alpha delta theta, where alpha is the coefficient of linear expansion, uh, coefficient of linear expansion, okay, thermal coefficient of linear expansion of that particular material. And this delta theta is what? Change in temperature. Same way, area A is equal to old area. New area A is equal to old area into 1 plus beta delta theta. And new volume is equal to old volume into 1 plus gamma delta theta. Okay, so this we have seen. Alpha, beta, gamma are thermal coefficient of linear expansion, aerial expansion, volumetric expansion respectively. Another point which we have seen is when there is a change in dimension due to temperature, then definitely for the cases like a simple pendulum, there will be a loss or gain in time, or there will be fractional change in time period and all. So dt by t is the fractional change in time period is equal to half into delta L by L, that is fractional change in length. So fractional change in time period is equal to half into fractional change in length, or loss or gain in time is what? Half into, okay, delta L by L into the time. Okay, for t time, capital T time, this much change in time period. Okay, another point is what? Suppose fractional change in time period is equal to half into delta L by L is what? Strain. So here we can say this is thermal strain. So for thermal strain, we have already written half into alpha delta theta. Okay, so these many things we have seen. Now we will do some problems based on all these, based on the expansion of linear expansion, aerial expansion, volumetric expansion, everything we will see. Okay, so here come your first question. Okay, right. So what they are asking is a rectangular plate has a circular cavity as shown in the figure. You can see here C diameter is shown in the figure. So a rectangular plate has a circular cavity as shown in the figure. If we increase its temperature, then which dimension will increase in the following figure? Okay, so you can answer now. Okay, pause the screen and think for yourself, and you please have your own answer. Okay, then verify the answer here. Okay, so one thing we are sure that if area expands, okay, definitely this dimension A, that length will expand. Then we are quite sure about B also. Length will expand, breadth will expand. What about that distance D? Overall distance increases. Okay, at least some of you might have not understood that D also will increase. The confusion comes for most of the students is like, suppose if this is a rectangular lamina or any plate, if this is a cavity, normally we may think like expansion can happen inwards also. Okay, so with this thought, some of you may answer A, B, D. We'll stop there. So this is wrong. Expansion will not happen inside. The reason is, when temperature increases, the movement, the vibration, the kinetic energy of the molecules will increase. So actually, when why it is increasing, because it need more space, or the distance between the molecules should increase. For that purpose only it is expanding. If it expand innerwards, what will happen? The molecules will come closer. Okay, molecules will come closer. Okay, so it is actually the reverse effect of the intention. Okay, see, inward expansion bring the bring the molecules closer. Okay, okay, so molecules do not want this. Okay, it doesn't want, they don't want to come closer. Okay, so molecules don't prefer to be closer. So inward expansion does not happen. Okay, so cavity size will increase. Okay, so you can note this. So inward expansion happens, molecules will come closer, so that is not preferable for the molecules. So what will happen? Outward expansion will happen, and so the cavity size also will increase. So the correct answer is A, B, C, and D. Option B is the correct answer. Clear? Fine. We'll move to the next problem. Okay. So here, suppose if there is something like this, okay, a ring like this. Okay, so there is a gap here. There is a gap here. So when we increase the temperature of this body, if we increase the temperature of this body, what will happen to the gap? So same case is the thing here. If it expand, okay, inwards, here what will happen? Molecules will come closer, so they don't prefer it. So answer is gap will increase. Gap will increase. So if we increase the temperature, okay, all the cavity, gap, everything will increase. Clear? So this is another one. Okay, what about this question? What is the percentage change in length of 1 meter rod, iron rod, if its temperature changes by 100 degrees Celsius? Alpha for iron is given as 2 into 10 raised to, here this will come as -5 per degree Celsius. Okay, so percentage change in length. Okay, so percentage change in length is what? Change in length divided by original length into 100. Okay, percentage change in length is nothing but change in length divided by original length into 100. Okay, so what is change in length? Okay, based on alpha, delta, theta, and all. Okay, change in length is alpha, delta, theta. Okay, what strain, thermal strain. So delta L by L is equal to change in length is actually what, L into L naught into alpha delta theta. Okay, see, L is equal to L naught into 1 plus alpha delta theta. So L is equal to L naught plus L naught alpha delta theta. So L minus L naught is equal to L naught alpha delta theta. So just a change in length means L naught alpha delta theta. If we need thermal strain, L minus L naught by L naught is alpha delta theta. This is nothing but change in length by original length. So alpha delta theta is that into 100 will give us what? Change in percentage change in length. So alpha is given as 2 into 10 raised to minus 5. The change in temperature, if the temperature changes by 100 degree, then that into 100 again into 100. So 0 0 0 0 4 zeros. So if we cut with this will become 10 raised to minus 1. We will be getting 0.2 percentage. This is the answer for this question, option D. Okay, clear. We will move to the next problem. Okay, another problem is a concrete slab has a length of 10 meter on a winter night when the temperature is 0 degrees Celsius. Okay, find the length of the slab on a summer day when the temperature is 35 degrees Celsius. Linear temperature coefficient of linear expansion alpha of concrete is given 1 into 10 raised to minus 5. So this is actually minus 5. Okay, 1 into 10 raised to minus 5 per degree Celsius, not 5. Okay, please correct it. Okay, so find the length in a summer day. That's it. So new length is equal to old length into 1 plus alpha delta theta. Direct formula substitution. So the original length was how much? 10. So 10 into 1 plus. So here alpha is 1 into 10 raised to minus 5. So the change in temperature, it was 0. Now it is 35. So we can write 35. Okay, so 1 into 10 raised to minus 5 into 35. So this is nothing but 10 plus, okay, 10 plus 10 into 10 raised to minus 5 plus 35. So what will happen? 10 plus, this is going to be 10 raised to minus 4. So 0.0035 will be this term. Correct or what? So when you add, we will be getting 10.0035 meter. So this much change will happen. Very small change. Okay, 0.0035. Okay, clear? So small change will happen if we change the temperature. Okay, so if this is in meters, if we convert into millimeters, we can understand the change is reasonable. Okay, all right. Next problem. Okay, there are two spheres of same radius uh, and at the same material, but one being solid and the other hollow. Which sphere will expand more if they are heated to the same temperature? Okay, so I think currently we are quite sure that this will expand. Okay, there is no confusion in that thing, it will expand. But if they are same material, the confusion is whether they will expand equal in equal dimension or one will be more. Likewise, that is a question. Okay, so what is the answer for this? You should also have an answer. Okay. Okay, so in this case, in this question, we can have, if we give this one A, this one B, okay, options can have A will expand more, B will expand more, both same, okay, or otherwise no enough data or none. Likewise, we can give. So here, always when we increase the temperature, we are getting a photographic expansion, we can say. Expansion will be photographic. So if they are same material, definitely whether they are there is a cavity or whether there is a no cavity, at least this outer ring should expand as equal as the solid one. So the answer for this question is C. Okay, both will expand equally. Okay, because this is also both are same material. Okay, so since there is no inward expansion, definitely this is going to be again same expansion. Clear or what? So our next question is, for an ideal gas, find the value of gamma at a constant pressure. So we need to find the the coefficient of thermal expansion for volume. We need to find. Okay, and they have given like this is an ideal gas. So let us try in this way. PV is equal to what? nRT. This is an ideal gas. So in this pressure, nr, all these are constant, number of moles and universal gas constant. So P delta V is equal to nr delta T. If the volume changes, temperature changes. Okay, so they are the variables. What we need to find gamma. So suppose if new volume is V dash and old volume is V, then we know V dash is equal to V into 1 plus gamma delta theta. So V dash is equal to V plus V gamma delta theta. So here change in volume is V dash minus V is what? V gamma delta theta. So change in volume delta V can be written like a V gamma delta theta, where V is the initial volume here. So I am going to substitute P into delta V is V gamma delta theta is equal to NR delta theta. Delta theta and delta T both are same, change in temperature. So delta theta we can cancel. So gamma is equal to what? NR by PV. And we know PV is equal to what? nRT. PV is equal to nRT. So I am substituting nR by nRT. Okay, so cancelling all that, I will be getting gamma is equal to 1 by T. So option C is the correct answer for this question. Okay, clear? Shall we move to the next problem? Okay. Yes. A pendulum clock of iron rod connected to a small heavy bob. A pendulum clock of iron rod connected to a small heavy bob. If it is designed to keep correct time at 20 degrees Celsius, how fast or slow will it go in 24 hours at 40 degrees Celsius? So we need to find the loss in time or gain in time. Okay. So either loss or gain, that is what they are asking. Coefficient of linear expansion of iron is also given. So how to do this problem? So we have studied fractional change in time is what? Half into fractional change in length. So here loss or gain in time is what? Dt is equal to half into delta L by L into T. So delta L by L is thermal strain. Already we have studied this is alpha delta theta. So we can replace this with the half into alpha delta theta into the time span. And time is given as 24 hours. 24 hours means 24 day into 24 hours per day into each hour 60 minutes and each minute is 60 seconds. So substituting all that, half into 1.2 into 10 raised to minus 5 into the change in temperature is 20 into 24 into 60 into 60. So just we need to simplify this. Okay, so already we have seen like for a day 24 into 60 into 60, it is always better to remember this value 86400. 86400, then substitute that and simplify, we will be getting the answer as 10.4 seconds. Option D will correct as come as the correct answer in for this question. Okay. Okay, so these are the certain questions on certain applications of thermal expansion on solids. Okay. Okay, students, so practice more problems from this area and study well. Okay, goodbye, good luck.